Hello, happy day. Okay, today we are going to talk about equilibrium. So turn to page 7 in your packet. So not 4, page 7. And we're going to answer these 3 questions and then draw some graphs right here. Okay, so first thing is equilibrium. Equilibrium is when reactions can go in either a forward or reverse reaction. So here's what this means. Right here we have these 2 half arrows. This is reactants, this is products. So the forward would be us going from reactants to products. The reverse is products to reactants. So one way to show equilibrium is by these half arrows. Another way is a double-sided arrow like this. And the third way is showing 2 arrows that are close together. So again, there's one way, 2 ways, and a third way. So here's this reaction on the bottom. The forward reaction is the green arrow as it goes from reactants to products. The reverse reaction is this maroon arrow or purple arrow going from products to reactants. Okay, on your paper now, go to letter B. And on letter B, the answer is equilibrium is achieved when forward and reverse reactions occur at the same rate. So what you're going to want to put down is this part right here, occur at the same rate. Now notice that rate is bolded. That's because that's the most important word in that phrase. Occurs at the same rate. We're going to talk about what that really means. Okay, and then this next part, this is letter A. In equilibrium, it has to be in what we call a closed system. So I want you to think about a soda bottle right here, okay? And each one of these has a lid, right? There's these lids. And so with the lid on, we have what's called a closed system. And that closed system, we can change energy in it, right? We can shake it. We can freeze it, we can increase the heat, and we can do that all in a closed system. But what about the amount of matter? So the amount of matter in here, okay? In a closed system, because it's a closed system and you have this lid on, you can't change the amount of matter. Now if we open up this lid and we take it off, bloop, okay, or we unscrew like a lid of a soda bottle, right? The energy, we can still shake it. We can still add or decrease heat. And then the matter, though, now, we can dump out the amount that we have in there. We can dump out some soda pop, or we can add some water back to the soda pop, or we can add fun little things like coconut flavoring or cherry flavoring or like coconut creamer. Or we can decide to just dump it out or drink it, okay? So the difference in a closed system versus an open system is that in an open system, we can change the amount of matter. And in a closed system, we can't. But both of them deal with energy. Okay, both open and closed deal with energy. So that, again, is letter A. Okay, and then letter C is this bottom one right here. Amounts of products and reactants are not necessarily the same. So again, what you're looking for is not necessarily the same. And again, we'll talk more about that as we see some pictures of some graphs. All right. Okay, this is kind of just showing you some more examples of what things look like. So if we're talking about a phase change, specifically like a liquid to a gas or a gas to a liquid, as we're going from a liquid to a gas, this is when evaporation occurs, right? This is evaporation. And going from a gas to a liquid is condensation. If these occur at equilibrium, that means they're occurring at the same rate. So the rate at which liquid is going to a gas, liquid to a gas is occurring as well. So they're occurring at the same rate. So to us, it probably looks like nothing's happening. Okay, another example is this one right here, equilibrium. Notice this beaker is in a closed system. As the gas is condensing, it goes to a liquid. As the gas is evaporating, as the liquid is evaporating, it becomes a gas. So this is a really good picture of what's happening in a closed system at equilibrium. And then there's this little joke on the left-hand side that I thought was kind of fun that you can pause and read. Okay. Going back to page 7, let's now look at these graphs on the bottom corner, these little lines right here. So right here, I want you to go ahead and draw that in your bottom portion. So go ahead and draw that on the bottom left-hand side, this graph right here. Okay. When you get done, I want you to notice where equilibrium is. Okay. Equilibrium in this case is going to be where the rates are the same. So if you've already done your lab, that's awesome because this will help you understand your lab a little bit better. But let's say that this is like 15 centimeters of water. Okay, this is like our lab that we did on Friday. And equilibrium is going to be where the rate equals out. So it's going to be somewhere in here. Sorry, my line's not very straight, but the rate isn't changing. So that's why in the lab, when I said you have reached equilibrium when you have 5 consecutive water transfers, this is what I was talking about. Notice how the products are at this higher amount and your reactants are at this lower amount, but the rate, they're not changing. So if we keep on doing our lab, we're transferring the same amount of water every time. Okay. Our next one, I want you to draw this next graph. Okay. And I want you to see where I want you to put a line where you think the equilibrium is at. Okay. And then let's talk about where that equilibrium is at. So on this one, the equilibrium, and I know you look at this and you're like, Ras, it says equal rates. So right here is where equilibrium. So on this one, the forward and the reverse rate are occurring at the same rate right here, which sometimes this happens. Sometimes it doesn't. In the lab, I probably had one group in every hour that this happened. So maybe their height of their water and both the reactant and the product can was 6 centimeters. This is usually, it doesn't occur very often. So it's usually a little bit, well, it just doesn't occur very often. Sorry, I can't think of better words. Okay, so that's what we're talking about right there. And that's how you show where equilibrium is on a graph. Okay, to give you some other examples on here, okay, equilibrium is all about rate. So in a bouncy house, there's usually a maximum number of people. So if equilibrium were to occur, these are just some examples outside of a lab setting, would be like if when 2 people leave the bouncy house, then 2 people can enter the bouncy house. That would be an example of equilibrium. So 2 people enter, 2 people are leaving. Okay. On a ski lift, let's say you're up at the face at the Beaver Mountain, and you have the ski lift, and you can only have 2 people in a chair, and it's a crowded, busy day. So the ski lift is just running, and it's staying at full capacity. So equilibrium on here would be when 2 people get off at the top of the lift, and then at the same time 2 people are getting on. Okay, that would be equilibrium. This one, if you've ever had those trick candles that you blow them out and they come back on, this would be like you're blowing it out and it blows out 3, and then at the same time 3 come back on, and you blow it again and maybe 4 come out this time, and then 4 come back on. And so these are just some examples of what equilibrium would be like in a situation. Okay, so now let's talk about this right here. This right here is an example of what's happening at equilibrium. So in a lab setting, here we go. The height of our, let's just say this is water, is the same. Okay, you can see that right there. And then something happens and it gets disrupted. So disruption in chemistry is either going to be concentration, which is the amount. So like maybe I'm adding hydrogen, or I'm adding oxygen, or I'm adding water, or the removal of something. That's concentration. Or it can be changing temperature, or it could be changing pressure. So there's some kind of disruption that has happened. And now look at this picture. Okay, in this picture, we're noticing here that we have a different amount of water in this left container. Okay, so the system's on equilibrium. Then the system doesn't like that. The system doesn't like to not be in equilibrium, and more reactions are in equilibrium than we think. And so what happens is it will respond to that system, and it's going to create a new equilibrium. So here we have this new equilibrium, and notice that it's not the same as it was before because a new equilibrium has been established. Sometimes it's the same as before, a lot of times it's different. And so this is kind of like us. If we relate equilibrium to people, sometimes we get stressed, right? And we react differently to that stress. Some people might sleep, some people might go exercise, some people might eat too much or not enough. Some people, you know, want to take out their aggression, maybe go and hit a punch bag. Okay, there's all different ways to deal with stress. Some people organize and they make a list, or some people are just like, you know what, whatever this is, I'm just going to get it done with, and I'm going to be done with this stress. So this is what happens to reactions. They don't want to be stressed out. They don't want to be disturbed, and so they are going to create this new equilibrium. Okay, now turn to page 8. Sorry, this is now page 8. And we're going to talk about the first two little things up here. Okay, so the first thing is that a system stays at equilibrium unless disrupted, just like us. Like everything's going fine, and then sometimes we get stressed out. So there's a man named Le Chatelier. Here's a lovely picture of him, and this is what Le Chatelier says. It says, if equilibrium is disrupted, the system shifts equilibrium to oppose the change, and then a new equilibrium is established. So go ahead and put that down on number 1 on page 8. Okay, then let's talk about this. Equilibrium is going to shift because of 3 things, and we've already kind of discussed this. Okay, but it can change in the concentration, which is just amount of any compound present. So that means like adding or removing hydrogen. We can raise or lower the temperature, or we can add or remove pressure. So on number 2 on page 8, these things that are bolded, this is what I want you to put down on number 2. Concentration, which just means amount, temperature, and of course pressure. Okay, that's it for our notes today. We will come back on Wednesday and do the rest of page 8. You also have a quiz that you will take today. I'll put that on Canvas. Okay, let me know if you have any questions. Thank you. Have a fantastic day.